is
Recording in progress.
Gonzalo Martano. From here, Gonzalo joined the FISC in 2021, first as a Juan de la Cierva fellow, and now he has Ramon y Cajal. And since January 2023,
Yep.
and before joining the FISC, actually he got a PhD from Universidad Complutense de Madrid, and then he has been postdoc and ICTP in Trieste, and something that I cannot pronounce, something like IQ in Vienna. And right now, actually, is leading one of the most innovative lines of the Institute about quantum stochastic thermodynamics and non-equilibrium statistical physics in general. So thank you, Lalo, for the seminar, and the floor is yours.
Thank you for the presentation. So today I am only going to talk about classical things, so not quantum, and in general about thermodynamics of computations. So perhaps you should not like focus more on your attention now in this subtitle of this talk, because this thing of unidirectional transitions, absolute irreversibility, and stochastic computation times, I will explain during the talk. So let's just for the moment focus on the main topic, which is just trying to combine thermodynamics and computations. So the main idea is that we would like to look at the relation between performing some computational task by some computational machine, like a Turing machine, like you can see here, and see what are their thermodynamic implications, or look at it with the lens of thermodynamics, as it was done perhaps before with the steam engine or all the heat engines. So this is in general a fundamental problem, but it may be also something important for the society. So because we had an exponential growth in computing from the beginning of the 20th century. So here in this plot here, you can see the number of calculations per second and per $1,000 during time, how this has grown. It's a logarithmic plot. So this means that there is an exponential increase. And this, of course, has been related to also an exponential increase in the energy that we need in order to perform all those computations. So in this other plot here, so you can see these different lines, which are essentially the consumption of energy of current technology for computation, using this benchmark of 10 to the minus 14 joules per flip in a bit. And if the same trends continues, we will reach like world energy production like in 2036 or 37 or something like this. And you can see also like other lines that will be, if we could reduce this energy per bit like to 10 to the minus 17, and this other will be just the Landauer limit, like the minimal amount of energy you will need in order to power these operations. So in general, it could be important to understand better what is this link between energy consumption and computing. And of course, not all computers have the same energy cost. So here, for example, you can see, so brains have a power of 20 watts, more or less, and you can compare this with a laptop or a supercomputer, that it will be much more costly. So having this in mind as a motivation, so let me just summarize the outline of this talk. So I will start with some introduction about the problem of so the link between information processing and thermodynamics. And then I will present our contribution to this field, which is essentially defining a framework for Markovian computations, where we could estimate dissipation in non-equilibrium processes. and taking into account different difficulties that may arise, like, for example, absolute irreversibility. I will explain later what is that. And also assessing computations that finish at some stopping times, some random times. And I will present some of our results concerning this, which are given as second law-like inequalities and fluctuation relations that apply to those processes. So the link between thermodynamics and information processing is old. It's not a new problem. It may be traced back at least to Szilard, who was the first to introduce an information engine. So it was a thought experiment. It was also coming from thoughts from Maxwell about the possibility to break the second law using some information. And this can be resumed in the following way. So what Szilard did is to consider some single particle gas in one box at some volume V0 and on outside temperature T. So the system will be in equilibrium. And then he thought, okay, what happens if I insert some wall in the middle? So then if I can see whether the particle is in one side or the other, or if some little intelligent being or demon can do that, then he could decide whether, knowing where the particle is, he could decide to expand the gas towards the opposite side of this box, then extracting some work and turning back to the original situation. In particular, in this case, it's very simple because so just from classical thermodynamics, you can compute how much is the work that you extract in an expansion, isothermal expansion, which will be just kT log 2, because this is the volume of the half of the box, and you have here the volume of the entire box, so this is kT log 2. So of course, that was like a paradoxical effect, because in this case, you will not be employing any work, but you will extract some kT log 2 per cycle. So if you do this once again, you will get a lot of work for free. And Szilard was thinking that it probably is inside this measurement process that some cost should be introduced in order to compensate for that, because obviously you cannot do that in the real world. But it was not until the middle of the 20th century that this problem was somehow solved by Rolf Landauer and later by Charles Bennett, who thought that information is physical, in the sense that you will need some physical degrees of freedom in order to process information. So so at the end, you can link this information, this abstract information, to physical degrees of freedom that you need to operate with. So doing that, what Landauer did is to calculate what will be the minimum amount of heat or the minimum amount of work that you will need in order to erase a bit of information. So the idea is that in the previous slide, we see that you have to measure, so you have to use some memory to store the result. And at some point, if you want to really close the cycle, you will need to erase that information that you store. So what means erasing information here? So you can, at this plot, it means that, imagine that this double work potential is just like two states of a memory. For one well, you have the particle in this well, this is 0, for example, and if this is in the other well, this is 1. So in order to erase information, what you need is to starting from some distribution in which you can be either in 0 or in 1, you will finish deterministically in just one of them, here, for example, in 0. So doing this process, this of course nowadays is done in the laboratories, like with very well precision, and because so they have very well control over these kind of systems. But the result by Landauer was that at least you will need to waste kT log 2 of work. This kT log 2 comes from the fact that you assume that the initial distribution is 1/2 0, 1/2 1. If you have another distribution, initial distribution, you can generalize this to have here just some the drop in the entropy that you have during the process. But okay, the point is that all these pioneering results that were very inspiring, but of course they are kind of limited because they reduce to very particular operations like bit erasure in processes in which the process is reversible, so it is quasi-static, means very slow processes, and also you will use equilibrium thermodynamics in order to assess for that. Instead, in real computation, we have many different kind of operations. The processes are in general fast, so they are irreversible processes, and you need non-equilibrium thermodynamics in order to assess that. So in general, the idea that emerged during the last, I don't know, 10, 20 years is that perhaps the development of stochastic thermodynamics, which allows you to treat very general non-equilibrium processes, in general in a small system with fluctuations, could be applied to computational tasks to see some light inside these problems. And here I just put some review from 2019, in which some of these efforts are discussed. Nevertheless, the conclusion somehow is that we have not yet some general theory of non-equilibrium thermodynamics of computation. So there are examples and so on, but there is not a general framework that we can just now apply. And this is where our contribution kind of tries to build, to get establish some more general framework, at least that allows you to partially assess some of the questions. So the main point for us is indeed connecting somehow computational science with thermodynamics, in the sense that in general, the computational science have a lot of machines or models in which describe different types of computations, like for example, Turing machines or finite state automaton, in which you have transitions between different states, you read some tape, you can write some tape, etc. But this is in general somehow disconnected from the physical implementations of these models, like a computer or, servers or whatever. And our goal indeed is to try to link these two worlds, in which you have all these physical implementation with a lot of physical degrees of freedom and some other symbolic computational states in which you use in order to do the actual operations for the computations. So the goal is to relate these two things, no? The thermodynamic cost of a computation and its function, no? What specific task you are doing. And this is so our work, which was done in collaboration with these three people here. There is David Wolper from Santa Fe Institute, Will Chacardes from the University of Colorado, and Edgar Roldan from ICTP. The idea here is to develop some theoretical framework that allows to handle this kind of some difficulties that were perhaps difficult to surpass before, like these things as absolute irreversibility, unidirectional transitions, and computational stochastic computational times. And we propose it like in a framework of Markovian computational machines, so Markovian dynamics. And we are able to derive some universal bounds and fluctuation relations that allow us to somehow bound the minimal dissipation that a computer needs to produce in order to do some specific, to implement some specific computational model. So in order to just give some idea of what I am talking about, let's consider one prototypical example, which will be here a deterministic finite automata that is fed by some input symbols. Okay, so here in the right you have a tape in which you have some symbols written that are input with some probabilities in order into the automata. The automaton, what does is that it starts at some states Q0. In this case, it's this. And it starts to get some symbols from the tape. So it gets a 1, transitions to this other state. Then it gets a 0, goes to here. Then another 0, perhaps turn back to here. The idea is that the functionality of this deterministic finite automaton are implemented by the fact that you may accept or reject some input word, depending on whether you reach the target or the accept state. In this case, it is Q0 again. So this is an example of a DFA that recognizes bit strings that are divisible by 4. So for example, if you get 1, 0, 0, this is 4 in binary numbers, so you will accept it. But if you get 1, 1, 1, you will still be here, so you will not, that will not be accepted. So the idea is that here we build a Markov process over this. So by assuming some probabilities to get the symbols, in principle, let's assume that they are IID. Then you can, from this diagram, you can construct a time homogeneous discrete time Markov chain that will jump between the states with these certain probabilities. So you can write down the probability of a given sequence of states of your automaton. That will be the initial probability to be in the initial state H0, and then the product of all the conditional probabilities to jump from one state to the next in the next time step. So at the end, here we are assuming a space of computational states. We call X and big X the total space. And we have these trajectories of this is a sequence of states that the automata follows during time. However, this is kind of disconnected, not to thermodynamics. You even may try to apply here stochastic thermodynamics, and you will not be able to. Also, because sometimes you will get unidirectional transitions here, so you will not have the opposite transition. So if you try to compute quantities, for example, like entropy production, that will diverge. So in principle, it's somehow hidden, the link between this and any physical implementation of this. In order to establish some relation, what we do is to enlarge the state space of our system. So let's now imagine that these computational states are some combination of physical degrees of freedom that are in a physical computer, so that we can have some larger state space Y and continuous time. And the idea is that when you marginalize over all these other degrees of freedom that are not the computational degrees of freedom, you will go back to the Markovian dynamics that I just presented before. So this is related to this embedding problem. So how to describe dynamics and Markovian dynamics using another underlying Markovian dynamics with hidden states, etc. And in principle, you can always do that if you allow time dependence in the evolution of the underlying underlying dynamics. So time dependence and extra hidden degrees of freedom. So in our case,
automata Markov chain. But in the automata, you have less information because you don't know which is the probability are in the first and in the one of the three. Description, one will be one, zero to later. But in the other, you have probability disposition of probability.
Yeah, we assume that the input symbols come with some probability that for the moment is IID distributed. Then we will see that we can have more general probabilities for that, also Markovian or. So yeah, the idea is to consider these extra hidden states and time, so that this Markovian process on computational states is implemented by some, so it's in the global space, is a time inhomogeneous continuous time Markov chain. So in principle, we don't need to assume it is Markovian, but for simplicity, let's do that. So in that space, you will have some transition rates, some transition matrix that depends in general on time. And since we would like to focus on digital computation, we will assume that this process is periodic. So we have some periodic driving in this physical space that is what you have in general in digital computers. And then what we like to do is to apply thermodynamics at that level. So of course, this will be plenty of details that you will not know, but theoretically you could do that. It's unpractical, of course. But you can assume that at that level, there is local detail balance at every instant of time. And you can write down what will be the entropy production at that physical level. So we know from a long time ago that this entropy production is related to informational quantities, such as, for example, the Kullback-Leibler divergence between the path probability of trajectories in this physical space and the ones in time reverse process. So here, y will be trajectories over all these physical state space, which will be huge, and also the time reverse trajectories when the periodic driving is time reverse as well. So in principle, this is all known. Now, yeah.
Why here and the thermodynamics? So what is the difference with respect to the previous smaller systems?
Yeah, in principle, because in principle here the transitions and everything is just coming from the input symbols and all these things. But here, so we are considering like what will be the underlying physical implementation in which all the transitions will be given by the fact that you have some external driving that is powering your system, and you have some environment in which this energy may be dissipated for doing all these tasks. Periodic is because digital computation is periodic. All digital computation is done with periodic signals. So all the input power is periodic. So you have always some quartz oscillator that gives you need that signal in order to do that. Yeah, like having a clock in the computer. This is just the reason is just was just that. Indeed, you may perhaps think in other cases in which this is not necessarily periodic, but we will need to. So that we will need to extend our formalisms. Yeah, but that modulates all the computation somehow. So whether it's a periodic process or given by a periodic driver. So it's the periodicity of the driving that sets the periodicity of the process. Okay, so then, so the next step is to then try to go back. Now we have this expression for the entropy production in this extended physical space, and then we would like to go back to our computational state space. So in order to do that, we can use a property of the Kullback-Leibler divergence, which is that the chain rule. So if you coarse grain now over state and state space and time, so like we're doing some slicing, you can obtain some marginal path probabilities for having the trajectories over the computational state space. And you can do that both for the forward process and for the time reverse process. So in general, you can be sure that you can always obtain a lower bound on this entropy production on the global space by just computing the same quantity over these marginalized path probabilities that correspond to our computational Markov chain. Here, the main point or the main problem is that in general, since you have to marginalize something that depends on time because you have this periodic driving or more general driving if you want, this quantity will, this path probability will not be the same as this one. And this is something that is problematic. No? Usually people when try to estimate entropy production in biological systems and so on, you do in non-equilibrium steady states. Non-equilibrium steady states, you always have, since you don't have time dependence, you always have that P is equal to this P tilde, and then you can kind of apply these kind of concepts in order to estimate entropy production, for example, in molecular motors and so on. And this has been done in several papers. Here it's more difficult because in general, you will not know what is this P tilde. It comes from this marginalization over this big space with time dependence and so on, that in general, you will not know if you don't know all the details of that. But then what we try to do is, okay, but let's, instead of assessing what is the whole entropy production of that process, or the whole coarse grain entropy production, let's just focus on some decomposition of it. So let's just go to some part of this entropy production. And in particular, we focus on what is called mismatch cost. So this is a decomposition, which in general can be done for very general cost functions. So if you have a general positive cost function with some properties, the entropy production fulfills that. For example, you can split this cost function in two terms, both of which are positive. This R term is called residual cost, and it's just the minimum of this cost over all initial states. And then the remaining part is what is called mismatch cost, which has this general expression here. So it's the curvature level divergence between the initial state to this distribution mu, which is just the one that minimizes this guy. And then the same quantities evolved over time after the discrete time process has been run. And we can be sure then that both of them are positive, that all the cost will be always greater or equal than this mismatch cost. And this is essentially what we want to apply for entropy production. So in our case, this cost will be entropy production, and we will get some lower bound on entropy production that just depends on what is this prior mu that minimizes the global entropy production. So this will apply for the case of periodic processes. So we can have this chain of inequalities. So entropy production in the extended state space of physical implementations will be greater or equal to the one that is coarse grained to our Markov chain over computational states. And this will be always greater or equal than this mismatch cost over all the cycles of the computation, which is just this expression here. We call this quantity intrinsic mismatch cost or intrinsic dissipation. That will be the minimal dissipation you will need in order to have these dynamics, the dynamics of these quantities that are not in general the best one or the minimal one that you can employ. So the good point of this is that all the messy physical details of the implementations and so on just get inside a single quantity, which is this distribution here. So and all the other things we can compute from just the dynamics of the discrete time Markov chain describing the computation. If you don't know what is this mu, you can even minimize over all these possible prior distributions, and then you will obtain like the infimum of these quantities, which we call minimal dissipation. Okay, this is everything at the average level. So it's the average dissipation or average entropy production, or a lower bound on this average entropy production. But we want to describe processes that are stochastic. And in order to do that, we have to build some version of this mismatch cost for stochastic processes. And in order to do that, we have to introduce an auxiliary process. So what we can do is to have so we can have this auxiliary process P bar with some initial distribution rho 0 bar and some transition probabilities, so that we will assume that the initial distribution is just the final distribution of the normal original process. And then for the transition probabilities, we will assume the following rule. So whenever we have a transition from I to J with some probability, transition probability P of J given I, in the auxiliary dynamics, we will have an opposite transition that will be given by this. So we will essentially, we will flip the arrow, flip the transition, and then wait by some numbers R here. These R's here are called, we call reference distribution, and they will in general be equal to this prior distribution or the minimizer over all the prior distribution that I discussed before. If you do that, you see that the logarithm of the path probabilities in the forward and in this auxiliary process reproduce this mismatch cost that I was talking to you before. In general, you get some stochastic version of this, and if you average, you recover the one that I showed you before. But just because of this form, you can also immediately have this kind of trivial fluctuation theorem also for this quantity. We will not use this very much, but just to point out. Okay, that will be the case if, so we will have this fluctuation theorem and everything like that if the system has support over the initial distribution of states. But this is not in general the case in computational process, because as I showed you before, you just start in one precise state all the time. So the start state of the automaton or whatever. So this means that we will have an effect that is called absolute irreversibility, which means that in general, if you construct this quantity, the exponential of minus this mismatch cost or the entropy production in general, this ratio of path probabilities can diverge, because perhaps you can go from some state A to B. So the probability to go from some state A to B in your forward process can be 0, but the one in the time reverse process can be non-zero. So in that case, you will have something that diverges here. So this is just one example. Right? For example, if you start and your initial distribution is a delta in this state B, and then you have some transition probabilities that allow you to go from B to B, from A to B, or from A to A, and you calculate now this auxiliary process you will see that since we start in the final distribution and we flip these arrows like that, now from A you can go to A, and from B you can go to both B to A and B to B. So we will have this situation, even if all the transitions are okay and you reverse all the transitions. So this is an effect of the support of the distributions at the beginning of the process. In that case, what has been shown in other papers, we reproduce this for the case of mismatch cost. You don't have the normal fluctuation theorem, but you have some extra term here, which is between 0 and 1, which in general is the total probability of having unpaired trajectories in your dynamics. And this gives you like a modified second law in which you have some positive term here that says that you cannot go like to reversibility because you have this kind of effect. No, so you cannot reach the reversible limit because of the presence of this term. Okay, so this is one thing that we will handle, and the other thing is to have stopping times. So because, as I was saying before, we are interested in what, for example, is the dissipation when a word in the finite automaton is accepted. So what is the dissipation in order to compute that word, for example? So that will require, so that will mean that, so every time we have, since these symbols come out random, so the time at which you will get the accepted state will be random, and then your trajectories will be not of a fixed time, but of a stochastic time. So in order to do that, in order to handle this thing, we need to employ martingale theory and extend it to this case of absolute irreversibility. So just as a reminder, so what are martingale or martingale theory? So it's a kind of class of processes, of stochastic processes that verifies this property here, which means that the conditional average of a quantity of a process, which is a martingale, given observations up to some previous instant of time t, just gives you the last observation. So this means that if you are observing stochastic processes up to some time t, and then you ask what is going to be the average value of this process in the future, then you can be certain that this average value will be just the last observation you did. It's like your best guess for the process afterwards. If you verify this property, you have many interesting properties, such as, for example, Dub's optional stopping theorem, that allows you to compute average of the martingale process at stopping times and relate them to the average at the initial time of the same process, which is a very powerful property because you can compute a lot of things here by just knowing what is at the beginning. Moreover, in this case, we are interested in submartingales and supermartingales, which are processes that instead of verify this with equality, they verify it with an inequality. And this, so of course, when you have submartingales or supermartingales, in general, you don't verify this Dub's optional stopping theorem, but you will get different things. Which we need. So we need to extend this theorem for a supermartingale, in particular the supermartingale that is given by this absolute irreversibility. So this kind of martingale theory has been applied before to stochastic thermodynamics, in particular to the case of entropy production. In some previous papers, there is a very large and exhaustive review of that has been published, I think, recently this year. And in our case, we have to extend these kind of things to the mismatch cost instead of the entropy production, and to supermartingales instead of submartingales, because we have this absolute irreversibility in general. So our strategy is to identify this supermartingale, which will be the exponential of minus the mismatch cost, plus or well, minus this quantity delta, which is called stochastic distinguishability. It's just the log ratio of the probability density of the system in the forward process compared to the time reverse process. So in our case, instead of the time reverse, we will have this auxiliary process, okay? But the concept is the same. What this measures is the asymmetry of the probability density under time reversal, okay? So it's essentially, if you start in some distribution rho 0 and you go forward in time, in general, you will reach some final distribution rho t. And if you go back in time with the auxiliary process, you will in general go to another distribution, right? So this measures how different are these two distributions at any given instant of time from in this interval. So what we can verify is that this process here verifies this, so that if you calculate this conditional average, you will get the same value as in the last observation, plus this extra term here, which is this 1 minus alpha. And this alpha term is essentially related to this absolute irreversibility, and is related to the probability of having unpaired trajectories during during this interval. So what we can say is that this is a supermartingale, because this is always less or equal than 1. And indeed, we recover a martingale when you don't have absolute irreversibility, so this is 0. So what we can show is that using this kind of supermartingale, so this is not general for all supermartingales, but it is true for supermartingales of this type, we can have a stopping time fluctuation theorem. So and this is the form that it takes. So it's the supermartingale that we have identified, the exponential of minus this mismatch cost and the stochastic distinguishability, and then this is equal to 1 minus this capital gamma, which is the total probability of the stop trajectories that are unpaired during so at these stopping times. Okay, so in reality, this is a very similar concept to what you obtain in the case of fixed time, but just is a little bit more complicated because you may stop at different instants of time during your interval. And this has, of course, consequences on the statistics of this intrinsic mismatch cost at the stopping times, and it will depend in general on the stopping time you choose. But one thing that you can immediately obtain is this second law at the stopping times. With now you have these two terms here. This term is, as in the case of fixed time, so it's similar to fixed time, so it's just a positive term. So it means that it will increase dissipation. So because you have this absolute irreversibility, the dissipation that you have to produce will be always greater. But instead, we have also this delta term that comes from this asymmetry under time reversal that can be positive. So we have minus this, so this can be negative. And this means that depending on how this is particularly, we can have some reduced dissipation at the stopping times. Okay, this is somehow one of the messages, so that if you go to stopping times, the dissipation of your computation could be reduced, depending on whether you obtain some condition that makes this positive. We can obtain also other relations for consecutive stopping times, which we will be interested as well, because, for example, we would like to see what is the dissipation between accepting one word and accepting the next one. So we can derive this inequality. And this, so this allows us to handle consecutive stopping times, so stochastic starting times and stochastic finishing times of your process. And so that the second law inequality associated to this will be this one, which will be related how much you increase your dissipation between one stopping and the other, and that will depend again on this stochastic distinguishability evaluated at these two stopping times. And we can, using this, we can then also obtain extra bounds. So we can also obtain an upper bound on this dissipation at the stopping times, and also another lower bound, which has the advantage that it does not depend on this absolute irreversibility term that sometimes is difficult to calculate, because you have to see what are all your unpaired trajectories in your process. And instead, this is just more easy to calculate. In reality, we have many more results. We have some other fluctuation relation, and we have also equalities and inequalities for the acceptance probabilities of words, for example, in models like the one I show you of the DFA. So let's just go to some examples. This is the example of the automaton that accepts binary multiples of 4. So we have this. This will be the original dynamics. This is the Markov process when you get like symbols that are IID with some probability. P0. So the P0 is the probability of symbol 0. P1 is 1 of minus P0. And then we can consider the auxiliary dynamics that will look like this. And we use as the reference distribution the invariant density of this Markov chain. So if we do that, we see that this bound, the first one I showed you, the second law-like bound, is saturated indeed. So here there's these dots, blue dots, are the entropy product where this mismatch cost as the stopping times. Then you see these other dots that are the same quantity but at fixed time. So that will be like the last time you wait before you stop. And you can see that this can be reduced indeed. No? So this is always lower than this. If you compute, so this quantity is shown here. So delta is positive. So this is why we can reduce this part here. And if you compute this plus this, which is this solid line here, you just get the equality in the bound. So it seems that the bound can be saturated in out of equilibrium. Another example is trying to go beyond IID symbols for the input symbols. So in this case, we consider this other automaton that in this case recognize binary multiples of 3. And in this case, we let the probability of the symbols to depend on the previous symbol you receive. So you have some probability of obtaining 0 given that your previous symbol was 0, 1 given that your previous symbol was 0, and so on and so forth. So, and then in that case, we can handle these kind of situations by going from the what will be just the model of the automaton, duplicating the number of states. So in this case, we will have these start states. We will have 2 start states now, because you can. So that will be kind of arbitrary. And then we can have all these transitions that will depend on these probabilities of having a 1 given that the previous symbol was 0, and so on and so forth. So we have this extended space. And if we calculate this mismatch cost in these cases, those are these dot lines here. And then the upper and lower bounds that I showed you before, you also see that they are, at least at in some range, they become also tight. Both the upper and the lower kind of delimitate quite well the range of values that this dissipation can take. This is another example for consecutive stopping times, like the times at which you will accept one word and the next word and so on, like for 1, 2, 3, 4 words, etc. And you see also like interesting effects, like from the second word to the third, you can have some reduction. And this is due to this difference on the asymmetry that in general are intriguing things that perhaps to explore more. So let me just go to the conclusions. So in general, so we put forward a framework in which we can estimate and bound the dissipation in generic Markovian computational processes at arbitrary stopping time and between these stopping times. So what are the advantages of this kind of framework is that you can apply it to even to processes, Markovian processes in which you have unidirectional transitions and these effects like absolute irreversibility. Your results are almost independent of the implementation details. Of course, they depend to the implementation details towards this minimizer of the entropy production, so this distribution, this prior distribution that you need. And your estimate of this minimal dissipation corresponds to somehow the intrinsic dissipation that will be needed, whatever your implementation is, compatible with that prior distribution, which is only due to how the dynamics over the symbolic or computational states is. So because you have some specific type of dynamics there, you will incur at least in dissipation. This is essentially so the idea is that this framework can be used to compare different models of computational task and assess what will be like the minimal cost that they will need. So it's a kind of relating function and the thermodynamic cost. And of course, our next step will be to really apply to, for example, different deterministic finite automaton that performs the same task, but for example, they may have different number of states. So it will be nice to see if the minimal number of states also leads to the less dissipation or not, and or even comparing like one task with another task, like with different automaton for other task. Also, perhaps going to or assessing this for more complex machines like Turing machines or, for example, push-down automaton. However, I have to say that just for the case of deterministic finite automaton, if you increase the number of states, you have the same computational power that any other more complex machine. So, principle, you will be able to implement any task also with the deterministic finite automaton with an infinite number of states, for example. Of course, there are also limitations of this framework. So what are the limitations is that we are assuming a time homogeneous dynamics over the computational states. So discrete time Markov chain without time dependencies. So this is, we assume that for simplicity, perhaps this can be raised, this assumption. We are assuming this, for the moment, this periodic driving in the underlying physical computer, which may not apply to many other ways of computation, like, for example, in biology or I don't know. And the main question is, of course, how do you choose this prior if you have not access to all these details of the physical implementation? So this is something that you may let for the engineers that build your computer, or you will be able, or you need to be able to try with different priors and then minimize over them or something like this. So that may generate perhaps some problems. So possible extensions of the framework will be using time-dependent transition probabilities for the Markovian, for the DTMC, that may correspond to non-periodic underlying driving, so more general drivings in your computer. And another thing that we would like to introduce is that for the moment we are always having examples in which you recite input symbols, but you don't write those these symbols in the tape. So you just recite them, and you do some operation condition on that, but you don't change that external memory. So an extension will be introducing also the management of external memory. So taking into account explicitly write information on this type and so on. And another interesting thing will be to consider autonomous stopping. No? Now we are talking about, okay, we are stopping at some point in which your computation reaches the state you want, but we are kind of imposing this. No, it would be nice to have models in which this happens naturally. No, like you have some mechanism that stops all the dynamics when this state is reached, and so on. And with that, thank you for your attention.